Shayan Mohanty, CEO of Watchful. Welcome to the Data Exchange podcast.
Thank you so much. By the way, it's Shayan.
Shayan. Okay, sorry about that.
No worries.
All right. So, company taglines are the future of data labeling. Short description on the website is a modern interactive solution that places the control of data labeling back into the hands of data scientists, machine learning practitioners, and subject matter experts. But actually, we're not here to talk about data labeling or Watchful at all, but we're going to talk about data management for unstructured data because Watchful has an interesting story in this area. But before we do that, maybe you can describe the type of applications that warranted the build your own instead of using open source or using cloud. So I imagine, as like any other startup, you tried not to build.
Yeah, absolutely, we did.
So what was that decision point?
Yeah. So let me first start by kind of describing the problem space a little bit. So this will kind of tease a little bit data labeling, but it's worth sort of considering because every solution should be built with the problem in mind. So when you think about just data labeling overall, the shape of that problem is typically like in status quo world, you get a sample of data, you hand that to some army of humans that then go label it. You get those labels back, you go run that through a machine learning process. And a lot of the time you end up looping back and you end up having to go back to your labelers and say, hey, I need to, make this better in some capacity. That's the shape of the labeling problem. Now, after that like 0 to 1 process, then you have like the 1 to 100, which is now I've got my machine learning model in production and I want to keep it up to date with, shifting constraints from the business, shifting sort of data from our users and so on. So I need to relabel at some interval. So that means that not only are you taking a batch of data initially, but you're retaking batches of data over time and retraining your model. And it has to go through exactly the same process. That's like the shape of that problem. Now, what we did was we took a good hard look at labeling overall, and we wanted to approach this from kind of like a first principles standpoint. So the first place I ran into the data labeling problem was actually at Facebook, where I was building a machine learning team and we ran into the problem of not having enough labeled data. And I mean, we had enough money to where we could hire our own army of humans and have them label our own data and so on. But we realized that they didn't have the subject matter expertise necessary to label it in the specific ways we wanted. And, we didn't have enough subject matter experts to do it. So we needed to figure out some way to automate this, right? So what we did at Watchful was...
So wait. So far, everything you've described, I can just put all of this stuff in an object store.
Yeah, totally. Yeah.
Right.
So if you wanted to, you could like pass around this like one single data set and just like hand it around to various people, right? You're absolutely right.
Yeah, right.
And that could live in an object store. So that's kind of like the first take that we had. It was like, look, we just need this data set to like move around.
So it seems like what you're hinting at is that at some point you want to do more things like automation, and things like that, interactivity. So what's the level of interactivity that's required in a modern data labeling solution, and why do you need a specific storage layer?
Yeah. So let's talk about the way we label data, right? So like historically, you look at a thing and you say, oh, that's payment related, or that's account related, or that's positive sentiment, that's negative sentiment, and so on. Very 1 or 0 type labeling. In order to automate that process, there's several different approaches. The approach that we ended up taking was a combination of several different machine learning techniques like weak supervision and active learning. So let's just zoom in on weak supervision for a second, which is just taking a large quantity of heuristic indicators of a possible classification and combining them into a label that has a probabilistic value. That's, in broad terms, what weak supervision is. So what a user has to do is create these heuristics, create these labeling functions, essentially, which means that they have to sit down, they have to understand the data, they have to interact with it, they have to be able to say, if these words show up in this particular order, then it likely means X, Y, and Z. right?
And for our listeners who aren't familiar, the academic tools tend to require them to write labeling functions, which are
Yeah,
short snippets of code, right?
exactly. Short snippets of code that noisily indicate possible classifications. So a concrete example of this could be like a simple Python function that takes in a row of data and says, if I see a curse word in it, then it's likely negative sentiment. Or if
But
I see
but
the word
uh,
payment.
but the flaw in this assumption is usually the domain experts don't know how to code in Python, right?
Precisely. That is exactly right. Hence our entire purpose to be. So um, that's exactly the issue. It's like a lot of the time these domain experts don't have the capability to take what's in their head and write it in a way that's like inherently useful in a programmatic sense. So that's where kind of like the translation layer exists. That's why our product exists, so that a domain expert can sit in front of our product and not have to think about Python or any of these other types of sort of programming languages. They just have to sit there and basically interact with the product, and we infer what the heuristic likely should be. But the side effect of
Oh,
all
I
this
see.
is,
I see. So basically, they're based on how they're labeling or behaving, you're kind of inferring these heuristics. And so therefore, the storage layer has to be fairly fast in order to kind of have this good user experience.
exactly, it needs to be extremely fast. And in addition to that, not only does it have to be fast, it needs to be fast to the point where you can run ostensibly like a query, which is one of these heuristics essentially. Because if you think about like these heuristics, it's really a search problem. It's like I'm looking for these words, and I want to indicate whether this is likely like indicative of my classification. So how quickly can I find the words payment? How quickly can I find all curse words across my data set? How quickly can I validate that? These queries have to be run extremely quickly, not just from a user experience perspective, but we do a lot of modeling on top of this. Like we're constantly simulating all the possible queries that a user might want to do based on their current interactions and based on their current behaviors, which means that if we're simulating one query every millisecond, which is already really fast, we're only able to, simulate 1,000 queries every second, which is actually not that much. So
So
we actually
what,
have to go down to, okay.
so what were the requirements for the system? So if I'm
Yeah.
the product manager for this system, I write the PRD. So what are some of the key requirements that jumped out?
Yeah. So here are sort of like the base assumptions. The base assumption number one is that this is fundamentally a small data problem, right? Which is actually counterintuitive because you'd imagine that this would actually be a big data problem. But in fact, it's a small data problem relative to how other data management solutions operate because you're typically operating on a fixed data set as you're like developing these heuristics, right? So small data, number one. Number two is you have to be able to grow labels on top of this data. And these labels need to be able to interact with one another. So as an example, you might want to do like a taxonomy. You might want to say that if something is very likely security related, then it's also very likely account related. So you have to be able to apply metadata to your data that then affects additional labels that are created. So your labels should be able to interact. And further, we have to be able to infer what the label should be based on a bunch of heuristics, right? And these heuristics are themselves producing labels, right? We can label a data set based on whether it matches heuristic A or heuristic B or heuristic C, but these heuristics are going to layer one on top of the other. And then we learn a label from that. And these labels can then interact in very complex ways. And I, as a user, might want to be able to query that. I might want to say, show me everything that has a very high likelihood of being account related. And that will in turn be affected by things that are security related, things that have other heuristics and so on. So it's actually this like cascading problem. And what we
So,
did, good.
so what other systems did you try to use before you gave up? Did
So
you look into like vector databases and things like this?
yeah, and like we looked at like roaring bitmaps. We looked at like bitmap storage. We looked at vector databases. Obviously, we looked at the standard like Lucene. We even looked at what Splunk was offering. We looked at all sorts of things. What we came away with was let's talk about like Lucene and that call to or that ilk of various types of search.
Right.
Like again, we see this very much as a search problem. So we looked at the classic search offerings, and they were all very, very good at problems where your data might extend past the boundaries of memory. So Lucene, Elasticsearch by extension, and so on are very, very good when your data is like very large and you want to search against that. And Lucene is specifically designed for things like full text classification, full text search, really, not even classification. And yes, that's like a use case that we support, but actually we wanted to be able to build something that was generic. So it didn't care if the data was text or images or audio or whatever. We just see it as bytes, and we're applying labels to bytes.
So in the case of vector databases, right? So they are presumably fast. The primitive is nearest neighbors.
Yep.
But the main ingredients are these embeddings and vectors. And there's a big, not a big, but there's enough activity around them that people keep innovating on the algorithm side,
yep,
but also on the system side. So where does that fall short?
Yeah, it's not that it falls short. It just solves a different problem. And you can use vector search in combination with Watchful. In fact, we designed it that way. So as an example, like what vector databases do really, really well is like similarity-based searching. Right? Which is a part of this problem. Like I want to be able to say everything that's very similar to this thing is also very likely account related or payment related or whatever. That's a fair query. But at the same time, I also want to just be able to say, hey, if it matches this particular complex pattern, then I want to label that as X, Y, or Z. Now, vector databases are very, very good at that search problem where that similarity problem, where Watchful is very, very good at like the actual byte level offsets of here's where your search query matched and didn't match, and it's extremely fast and so on. But you can use your vector database output as part of input to Watchful. If you think about Watchful at like a very base layer, under the hood, all the way down at the very bottom of the whole thing, all you have is just a bunch of bytes. That's it. It's just a huge run of bytes, which is your data. And we have offsets for where labels should start and end. And these can overlap. They can do all sorts of things. But that's really all it is. So at the heart of Watchful is this core data structure that is extremely optimized to interact with, which just has data and byte level offsets for labels.
And now, this works for so your target space is unstructured data, which broadly means text, computer vision, audio, right?
Yeah, audio, video, even time series in a lot of ways. Like really, we're not super we're not prescriptive of the type of data you bring in.
I guess what I'm missing is so the vector databases are great at nearest neighbors and similarity search. So then if you describe patterns and tags and things like that.
Yeah.
But you can turn those into embeddings, and so therefore aren't they also, can't you use those patterns then and put them in a vector database? No, it doesn't work.
You could certainly do that. Like theoretically, you could build this on top of any technology. I could build Watchful on top of pen and paper if I wanted to. I could have a stack of papers that indicates like, here's where my label should start and stop. But the user experience would obviously be terrible. So imagine the case for iterating on an embedding space. Like imagine having to build a set of labels, retrain an embedding, retrain that again off of a new set of labels that now have a new dependency, and then like trying to continually iterate on that class space. It becomes very cumbersome. You're basically stacking a data science problem on top of a data engineering problem, on top of a computer engineering problem. Like it becomes very cumbersome to try and iterate on that. Again, one of our requirements is that labels should be able to rely on one another, and you should be able to grow labels kind of arbitrarily over your data. So in that way, we don't care where your heuristics come from. So for instance, you could have heuristics that come directly from interacting with our query language, which allows you to do a whole bunch of things. You could have heuristics that come from other models, that basically say, here's where my classifications start and end. You could have heuristics coming from vector databases where you wanted to do similarity search and say, if this thing is very similar to this other thing, then I want to classify it in this particular way. But under the hood, everything gets stored in exactly the same format. It's just a run of bytes that has offsets for labels. And we know how to interpret those offsets. We know how to use them. So that's kind of like the core piece of this. And it's not that vector databases are bad or can't do what we're doing. It's just that we designed this for a very specific type of user experience. It needs to be fast. You need to be able to iterate on it very, very quickly. And it needs to be able to be simulated, basically. We need to be able to suggest what the user should be doing at any given point. And these are really important properties.
So when we last spoke, I got the impression that while this system is bespoke and very specific to your use case, you seem to think that other people may appreciate a system like this, so much so that you guys are considering open sourcing it.
Yeah, yeah.
So what? So besides your use case, have you guys thought about? So let's say you open source this. So when you open source this, you would have to explain. Okay,
How other
so
people use it.
this is how you this is where this might be useful.
Yeah.
So in the case of vector search, vector databases, then they just say it's for search, and anything that has kind of a similarity underneath and nearest neighbors, right? So this might be appropriate. So how would you describe the system?
Yeah. So we have a couple ideas, and obviously this is not an exhaustive list, but the most obvious one is just like a core. Well, let's talk. There are like a couple layers to this, right? Like the base layer is this like core data structure that everything is built off of, which is this like sequence of bytes with label offsets. There are interesting properties about this data structure. So one is you can compute labels on top of these heuristics, right? So it's like it services quite well for our weak supervision needs. But the other nice part about it is if you think about like a typical labeling problem, you've got like annotator A and annotator B who could be looking at exactly the same data, but could produce different labels. And you need to figure out a way to merge those. So the interesting bit is that we've got a data structure that allows you to merge and split very, very easily and very quickly for like arbitrarily sized data. So you can bring several people's insights into one single source of truth. There's also like very fast indexing into it at like arbitrary levels. So you might want to classify entire pieces of text, like full rows in a database. And in the same exact project, you might want to index into specific tokens and say, this run of tokens is actually someone's name, and you want to label that. So we also have the ability to index like at arbitrary depth, which is another thing that a lot of search things don't really offer in quite a nice way. So that's like the core data structure. And even if we just open sourced that data model itself, that becomes very quickly, or it could become very quickly, like a common language amongst several different things in the MLOps ecosystem, right? If you think about supervised machine learning in general, a lot of the work that is done is fundamentally comparing one data set to another data set, right? Think about like, I want to build a confusion matrix. What am I doing? I'm taking a data set that was held out, running it through a model, getting the model's labels and comparing that to hand labels that a human did, right? That's just data set to data set comparison, right? If I'm trying to merge the work of two different people in labeling, that's data set to data set comparison. If I'm trying to track drift for a model, that's data set to data set comparison. I want to compare what my model did now versus what my humans are doing. If I want to track like model versioning and performance of a model, data set to data set comparison. I want to track like my current model's iteration versus an iteration before.
So you're saying one use case is a way for you to, even before you train a model, compare two data sets.
Yeah, very quickly and be able to like really index into it and really understand like here are the bits that are correct, here are the bits that are wrong, and have like a common language for doing this across systems. So it doesn't matter if I'm talking to Watchful or if I'm talking to some other model that outputs some data format. It doesn't really matter. There should be a common language that we're all like transacting into, where I know what my data is going to look like coming out one end. I know what my data is going to come out looking like the other end. And it doesn't matter what the data is. It could be text, it could be images, it could be video. It doesn't matter. Like our data format doesn't care about the actual data. It just cares about bytes, and we can compare them. So you can have an apples to apples comparison with exactly the same data format, regardless of the data structure, really like the data modality that you're dealing with. That's like one very obvious, like imminent thing that you can do. So kind of like a unified format for all things in the ML ecosystem that deal with supervised machine learning. This is not going to be everything to everyone, but it has certain use cases that are quite interesting. Then you go up a layer, which is like the query interface and our ability to run queries against this data structure very quickly. And that becomes very interesting because now you get into use cases where not only do I want a common, like a universal way to describe data that goes in and out of my ML ops systems, but I really want to like poke and prod at it, and I want to adjust it, right? I want to say, hey, this particular interaction is not quite right. This relationship that was learned, that where the labels were produced, like the byte offsets that the labels are pointing at, are not quite right. I want to adjust that. So I want to shift that over. I want to enlarge the
So
bounding
when you
box.
say not quite right, the model wasn't right or the original label wasn't right?
Or both. Doesn't really matter. Again, we're not prescriptive. We don't care where those two data sets come from. So it could be model, it could be model humans, it could be whatever. But there's going to be some interaction. You know, part of our like thinking is that there is no such thing as ground truth. That's like oftentimes when you require a human to evaluate a thing and apply a label, you're introducing some amount of noise. So we don't prescribe like.
Is it noise or alternative facts?
Yeah, it's a little column A, column B, right? Depends on who you're talking to. But you know that's part of the problem. So like we can't just assume that one data set is correct and the other is wrong. We have to assume that both are probably right in some capacities and wrong in other capacities, and we want to help you find the parts that are correct or incorrect. And all of that comes down to like, how do I take two data sets and compare them, like put them together? How do I then drill into that data set that's now merged and figure out the parts that need to be adjusted? And that requires arbitrary levels of granularity, right? You could be talking about entire rows, or you could be talking about character-based segmentation. You could be talking about pixel-based. Doesn't really matter. But you need
So are you describing something that basically, if you were to categorize it, does it live in the world of data quality tools, or?
I think it more likely lives in the world of search. This is actually something that we've been grappling with a little bit, but everything that we do can be likened to a search problem in some capacity. So if you were to compare us apples to something else, it would be a search product.
But search, going back, and I guess I'm not, I'm just trying to play devil's advocate here, but search, you got similarity, nearest neighbors, that's vector databases.
It is.
Yeah. So then this system, presumably, like you said, does more or does something else.
Yeah, it's just different, right? So vector databases do similarity very, very well. What we do is we take like think like pattern-based search, right? Like the most obvious example is like regex, right?
Oh, I see.
That's a very dumb example. It doesn't have to be regexes, but just as an example, a regex, right? You want if you want to search for this one particular word or this particular pattern in text, you want that to be fast. You don't want to have to go index against.
Whereas the current nearest neighbors vector search technologies is around, here's an example, find me something very similar.
Yeah, exactly. Yeah, that's exactly right.
It's not as expressive.
Yeah, and the other thing is like, how do you get arbitrary levels of granularity in a vector-based search? So if I have an atomic unit, which could be like a row in a CSV, great. Then I'll create like an encoding against that. I'll index against that and write that onto my vector database and so on. And that'll work. So given a row, I can find all other rows that are very similar. But perhaps you're doing a conversational AI task where not only do you need like intent level classification, which could be like row level, you know, an entire conversation. I want to know, or let's say like a message. I want to know what the intent of that message was. Great. Like you can say, I know the intent of this particular message, so find me all other messages that are very similar. But now I want to do like entity level classification. I want to do something arbitrary. You know, I want to do like NER. I want to not only know the intent, but I also want to know the entity that it applies to. Now that you've thrown in this like brand new requirement, now what that would require you to do oftentimes, I'm not going to speak about all vector database, all vector databases, but in a lot of vector databases, it's up to you to decide like what level of granularity you want to be able to query at. So if I were to then throw this brand new requirement at you, then all of a sudden you're going to have to go through a brand new process to re-index all of the, let's say, tokens, if you will, you know, and you'd have to find a clever way to do that. That also encompasses like the conversational history and so on. Like just getting that data back into the vector database and then searching against that is a process. That's could be several weeks, depending on how intensive that process is. Whereas our system, while it doesn't let you do similarity search natively, you can bring in that similarity search from another vector-based, database and just say, look, these things
or even just a library like Face, right?
Yeah, exactly. We are not prescriptive of where that information comes from. All we do is we know here's the data, and it's just bytes to us. And we know where you want the label to start and end. And you could have several of these labels, and they could stack on top of each other. They could relate to one another. It doesn't really matter. And there could be lots of information that's present in that label. It could be based on similarity. It could be based on a pattern-based search. It doesn't matter to us. We consume that information. We make it queryable, and we make it interactive, and it's very, very fast.
So besides the data labeling space, so what other areas do you think have this problem of here's pieces of unstructured data, different labels, different patterns?
Yeah. There's several examples that come to mind, which will sound kind of counterintuitive, but take like fraud, for example, like transaction classification and monitoring and things like that. That sounds very much like a big data problem, but actually most of the time it's a relatively small data problem because you're not ever training on billions of transaction logs at a time. You're typically selecting a sample that makes sense and you're crafting that data to where you're able to like actually do something meaningful. So for us, it's very much a small data problem. So kind of the thought here is...
So is that fundamental to this in the sense that the system that you built for yourself is for a small data problem, and you have kind of this way of, formatting or encoding the data. But if someone wants to do that at scale, does the system only work in memory in a single server? You know what I mean?
So the short answer is no. There's no like real limitation in the sense that like you can only do this on one server and you're only limited to what's in memory. That is the use case that we designed for. However, there's nothing stopping you if you wanted to take this and make it distributed, like coming from someone who cut his teeth in distributed systems, like there's nothing stopping you from taking this atomic component and just like constantly flushing to disk and bringing in new data and having like several of these running in a cluster. Like you would need to build the orchestration layer around it, to make sure that you have the correct sharding scheme and so on. But like, as long as someone's willing to write that code, fine. We just didn't because it's not part of our core use cases. Like no one is sitting here training their models on billions of rows of data. And if so, they're using nation state levels of capital to do it. So for us,
so what's the plan in terms of so you folks think this can be useful to more than just you?
Yeah,
it's written in Rust, so it's a hipster system.
Yeah. And to be clear, we wrote it in Rust not to be hipsters. We wrote it in Rust to move fast, and I'm happy to talk about how Rust enables us to do that. But yeah, it's in Rust.
But so then, if you were to open source this, what exactly would you open source, and when do you think that will happen? Hate to put you on the spot. But.
Yeah, I mean, I knew this question was coming. So, like, short answer is we have lots of ideas. We don't have a definitive timeline. I'd like to open source something sooner rather than later. We just need to think carefully about what exactly that is for all the reasons that you brought up. If we're going to put something out there, we want to make sure that it's actually useful to people who are not just us.
Yeah, and that it's easy to describe the usefulness of it, right?
Exactly. And it should fit into like at least roughly a box that people already know about, right? So we've built this very interesting system that solves this problem really well, and we have components in it that we feel fit those requirements. We just have to be careful about where exactly we draw the lines. The second big thing that we have to consider is we don't want to put something out there that is not going to be maintained at some point. Like we don't want to yank the rug out from under anyone, So if we put something out there, we want to have all the intention in the world to continue maintaining that like into the future. So it needs to be something that's not, at a startup, you try a bunch of things and some things you want to keep, some things you don't. We want to make sure that as we're evolving the system, we have confidence that these pieces that we're open sourcing are in fact stable, that people can rely on them for years to come, and that we will continue building on top of them, but we're not going to like degrade the foundation. So that's another piece that we have to consider before we open source. So that's the properties. Let me talk about what we could be open sourcing, some ideas that we have. One idea is open sourcing the data model itself. So the data structure, the way...
So this would be the equivalent of like Delta Lake or iceberg format, right? So
yeah, something like that, where it's like, here's a serialized form that allows you to store on disk very efficiently, and here's how you read it out into memory, and here's how you interact with it, right? And like some libraries to wrap that type of interaction in a nice way. So it would be like the primitive storage engine for like an actual database. The second tier that we could open source is the actual database itself, right? So storage engine plus like the query language and the way you interact with it, and sort of like the query dispatch engine and all this other stuff. The third thing that we could potentially open source, which we're still kind of debating, is the way we go about simulating these suggestions. And that's actually kind of an interesting bit, because because of how fast our engine is, we're able to simulate many thousands of queries in a second, because all of our queries transact in sub-millisecond latency. It's like a requirement for our system. So our suggestion engine is actually quite interesting. There's a lot of statistical stuff in there that could be open sourced as well, and like various types of libraries for different types of like query generation problems. And it's not limited to just our query language. Like you can basically load any sort of grammar you want into it, and it'll suggest stuff based on user interaction. So that's another thing that we're considering potentially open sourcing. But again, we want to make sure that whatever we decide we open source, it has legs, that it's going to stay around for a long time, that it's something that we intend to invest in for a very long time. We're not going to degrade the foundation, so that people can actually trust it.
So have you and your team had conversations with other engineering teams? And by that, I mean, if you look at the world of vector databases and vector search, it's not big, but there are people working on it all over, right? Mm-hmm. Different companies, different countries, and so on and so forth. So in this case, what would be the natural community that you guys could start having conversations with, so that, let's say, for example, you open source the storage format, then it'll be more than you that kind of comes out when this gets released, right?
Yeah. So, I mean, look, from a vector database standpoint, like we're pretty intimately familiar with that space, just because, as you mentioned, it's a small world and there's a lot of overlap with the world that we play in. Yeah. So, I know the Pinecone guys pretty well. We've worked with Gina before as well, which is another group. They're not technically a vector database; they plug into vector databases, but nonetheless, it's like a neural search company. Short answer is I'm not quite sure yet, like where exactly this would plug in. My inclination.
Like who's the natural community?
Yeah, I'm thinking it'll likely be like data processing overall. Think like the stream processing folks. Think like the search folks specifically. There's obviously a natural overlap with machine learning, and like our inclination is very much that, look, this is a task that is done all the time in machine learning overall, like comparison of data sets and being able to interact with them in this particular format. So we would very likely want to play into like the MLOps space, but there isn't something that already exists like this in MLOps.
You need to plug into some existing label. Like, are you like data quality? Are you like lineage? Are you know what I mean?
Yeah, and right now we don't really have those answers, because we didn't design this to be open sourced. Like we didn't design this as, oh, we want to go out and build a brand new X. We didn't go out and say like, oh, like we just want to go build something new. This was born out of a set of requirements that we discovered by really trying to solve the labeling problem from the ground up. And as a side effect of that work, we've discovered that what we've built seems to be more widely usable than just what we're exercising it for. Now, we'll have to do a little bit more thinking, which is why we haven't open sourced this yet. Like, we still have work to do to make sure that like we understand what community we would be building around this, who the right target audience is for this, what the, you know, length and breadth of the different types of use cases are all the time, that there is a lot of interest in sort of seeing this engine out there in the world because other folks have ideas. So, you know, there's still more work to be done for us to figure out exactly what community we play into, but we are eager to find that out.
So for people who work in or even run their own small startups, they might be wondering, so why open source it at all? Why not focus just on running the startup? So what's the upside for a startup like yourself to get into this open source game?
Yeah, and that's a very, very good question. So there are a couple of reasons. One is like this kind of overall need for this type of technology in like especially the MLOps space, which is still relatively nascent. We believe pretty strongly that there should be, I guess just to frame it correctly, we don't believe in end-to-end. We believe in best in breed. So being able to design best in breed products that can plug together like Lego blocks. That plug together bit is still ill-defined. Like not everyone has decided on the set of data formats that everyone adheres to. If you look at Kaggle, for instance, like across computer vision use cases, even like everyone has a different data format for how they present that problem. So like we feel pretty strongly that there's room for kind of like a unifying data structure, data format to sort of meld that whole.
That's different than best of breed, though, man. Because best of breed means I'm maintaining multiple systems, and why would I want to do that if I can get something that does the same job end to end? But the file format, that's a different thing. I mean, the file format could be something that goes from end to end.
Yes. So I guess what I'm trying to say here is you can put together several best in breed products as long as they all talk to each other. Right now, you can have several best in breed products, but they don't all talk to each other natively. And that's the bit where this file format would be the glue. That's sort of the idea. Now, end to end then has the argument that, look, you don't have to worry about that. We just go end to end. And that's fine. Like there are going to be some folks who prefer end to end versus not. We, you know, come from backgrounds where we certainly lean more heavily on the best in breed side.
Well, you're in Silicon Valley, man. Come on.
That's right. So we lean we bias very heavily in that direction. In order to,
but if I'm an enterprise somewhere else, and you know, I have a solution that takes care of data processing, storage, and then can do the machine learning, that's quite compelling, right? So,
I think this is an interesting conversation that we should definitely have. But outside of like the end-to-end versus best-in-breed thing, the other like very obvious like reasons why we would do this is number one, recruiting. We found that lots of very strong engineers actually care a lot about like contributing to the open source communities, be able to support open source software in general. We have lots of like very strong open source advocates on our team already. So it becomes like a very good recruiting tool if we have a portfolio of things that we support in the open source world that are well adopted. And the second is actually as like another kind of marketing channel, quite honestly. Being able to put software out there that people use and love, that they're not necessarily paying for, but plugs into this other thing that we do that happens to be commercial, is a tried and true way of generating net new revenue without necessarily needing to invest in like, you know, B2B sales teams and inside sales and so on. You can just kind of put it out there. And as long as you're managing and maintaining the community correctly, it will yield dividends. So
I can see the appeal, as you point out, right? So maybe there is a way for you to insert yourself into this MLOps conversation, which, by the way, MLOps is a terrible space to be in. There's so many companies; it's so confusing.
It's very saturated.
But on the other hand, you self-describe the system early on as very searchy. So why not evangelize this technologies within the search community?
Yeah, we sure could. So again, this is just homework we have to do ahead of open sourcing. We don't know yet which groups will find what we're doing like most interesting. Because again, this is born out of a real business problem. We just wanted to solve the labeling problem. That's what my company does. We didn't set out to build open source software. Open source software happens to come out of things that we happen to solve internally. So before we open source, we'll want to make sure we do that research and we do that homework to make sure we understand which communities would likely see the biggest benefit from this. But I think you're absolutely right. Like, the search community would probably care about this a lot. I have a feeling that the ML community would also care about this. But we'd have to be very careful about how we go about addressing potentially disparate communities. So, yeah.
So I have the names still ready to go.
Then I know who to talk to.
So for the file format, it's called watch file or watchfs. For the database, it's watchdb.
Yeah, love it.
Right.
I'm gonna go quickly trademark that before you can.
Watch file. Yeah. And with that, thank you, Shayan.
Yeah, of course. Thank you, Ben, for having me. This was a lot of fun.